Hi, this is our IC Engine Week 2 update. So as an introduction, the Generative Energy Systems Incorporated has built an IC engine and has asked Burdell Inc. to determine system parameters like the flywheel friction, flywheel inertia, and the work of the air, and has also been tasked with determining control for optimal power generation of this motor. As an overview of our progression, every week the group is to calibrate the force transducer and create a graph and equation as shown on the right. In week 1, the friction work and flywheel inertia were determined. In week 2, which is this week, we calculated the work of the air and the uncertainty. And in future work, we will simulate combustion with air injection during the power stroke. So in week 1, we collected data with the head off and no pressure, and we were able to determine the work due to friction by integrating the motor torque versus angular position at steady state. And also we were able to calculate inertia of the flywheel using the acceleration of the motor. This slide shows our week 1 results with the calculated inertia of a single flywheel plate as well as the inertia of our crankshaft. We also have values for the frictional work and frictional torque at the different speeds and with different masses added.
In the second week of experiments, we investigated the first four-stroke cycle of the internal combustion engine. We first recalibrated the force transducer by placing and removing mass plates and recording the voltage outputs and performing a linear regression similar to the previous week. Unlike last week, after calibrations, we collected the data with the engine head on, so the work done by the air needs to be analyzed. We collected 2 groups of steady-state angular velocity data with and without the flywheel at the end of each of the engine and record each group of data at high, medium, and low speeds. To analyze the work done by air in each stroke, we measure the work done by the motor, work done by the friction, and the flywheel angular velocities, and we calculate the work done by the air using the following equations.
From our results, we were able to determine that the kinetic energy term went to 0 because the angular velocity at the beginning of a stroke and at the end of the stroke were equivalent. So we were able to determine that the work due to air was only a result of the work from friction and the work of the motor. We then had to break up our data into the 4 individual strokes, which we started by first finding where the compression stroke occurred, which was determined by where the dip occurred, and we knew that because each stroke covered a distance of pi radians, we were able to work backwards and find each individual stroke from there. From that, we were able to determine how powerful each stroke was and how much work was done per stroke. Here are the 6 graphs that we generated from the data that we collected. We have data for all the velocities, low, medium, and high, and with a flywheel and without flywheels. What we find is that the data without the flywheels is very easy to determine where the strokes occur because the dips are very clearly visible, especially at low velocities. It's harder to see that when there are multiple flywheels because the energy from the flywheels is able to offset the work due to the motor when the motor is in the process of providing work into the system. It should also be noted that the data that we wanted should have looked with a dip coming up into a steady state situation and then dipping again. Unfortunately, due to some issues with our encoder and overall shakiness of the IC engine itself, our encoder readings ended up being less than desirable, and so we ended up with values that weren't exactly what we wanted to see. From our data, we were able to calculate the experimental work from the compression stroke and the experimental work from the power stroke and compare it to our theoretical work from both strokes. We found the theoretical work for each stroke. Compression is negative 15.4 joules and power was found to be positive 15.4 joules. Overall, without the flywheel, the work and the theoretical work were pretty similar. Unfortunately, once flywheels were introduced into the system, the work experimentally calculated and the work theoretical started to differ considerably. This is most likely due to the fact that the work experimentally with the flywheels was being offset by the angular velocity and angular momentum of the flywheels continuing to spin. So we were unable to get a proper reading on the work from the motor. As a result, it was harder to get a more accurate set of data when it came to the work with the flywheels as opposed to the work without the flywheels. It's good to look at sources of error and see where our data could have been better. Our expected data was supposed to look like a dip at the end of the compression stroke and then come to steady state before dipping again at the end of the next compression stroke. However, our collected data, while looking somewhat similar, did not manage to meet those desirable outcomes that we wanted. This was most likely due to the fact that our IC engine setup was prone to a lot of shaking, which ended up affecting our overall encoder values, which ended up affecting the data that we collected. So in the future, we would try to minimize this external vibrations and try to keep the motor spinning stably, which would ultimately help us get better data that's closest to what we would expect.
This week, the team also conducted uncertainty analysis at low, medium, high speeds, found the torque calibrated uncertainty measurement and the angular displacement per encoder bin uncertainty. And using those two values, we were able to calculate the combined uncertainty of the work of the motor, which will then be compared to our W discrepancy term.
So to review where we are now after week 2, we took data with the head-on and no pressure from air injection, and we found the work by air for each stroke. The model says that the intake and exhaust should be 0, and that the compression and power should follow adiabatic compression. We compared the model to the experimental work from the air to get W discrepancy as a goodness of fit for the model to the experimental setup. The plot on the right represents our best trial of data for the low velocity and no flywheels. Section 2 represents the compression stroke, and it is negative work on the system. Section 3 shows the power stroke, which is positive work on the system. And sections 4 and 1 represent the exhaust and intake strokes, which should net to 0 work. Now we can compare the model to the experimental results to find the discrepancy term, where W discrepancy is equal to the work of the air from the experiment minus the work of the air from the model. Accurate modeling will have a small discrepancy. We also assume that the uncertainty from the air is equal to the uncertainty from the motor from the experiment. We can use this in conjunction with W discrepancy to evaluate the IC engine modeling. If the work discrepancy term is larger than the uncertainty of the work from air, then we know that the model does not accurately represent the experiment and that our instrumentation is good enough that it falls outside of the bounds. If our work discrepancy term is less than the uncertainty of the work from air, then we can assume one of two things. The first being that we have a large uncertainty and that our instrumentation is not good for the way we are trying to measure the experiment. The other conclusion is that if the uncertainty of work from air is small, then our instrumentation is good for the experiment, and W discrepancy falls within this and represents a good model for our experiment. Now, comparing the work discrepancy terms with the uncertainty of the work from air, we can see that in all cases, the work discrepancy term is greater than the uncertainty of the work from air, showing that the model is not a completely accurate representation of the experimental setup. The conclusion can be drawn that we have good measurement devices for the experiment, but the model falls outside of these bounds. Moving on to week 3 for the experiment, we take data with a head-on and pressure injection. We will create a total engine model for each stroke in the pneumatic injection operation, which changes the model for the power stroke. Now we have isobaric compression between the piston positions 2 and 3 for the power stroke. The rest of the power stroke is still modeled using the adiabatic compression. We will then compare the work discrepancy and the uncertainty of the work from air, similar to week 2, to conclude on the model discrepancy from uncertainty for the engine in full operation. This concludes our update for week 2 of the IC Engines Lab. Thank you.